Alright, as promised, here are some gas law problems. These all come from your textbook. The numbers on the problems are all from Chapter 5. Alright, so here's problem 19. A gas occupying a volume of 725 milliliters at a pressure of 0.97 atms is allowed to expand at constant temperature until its pressure reaches 0.541 atms. What is its final volume? In a great many of these problems, the best thing you can do is to pull out all of your variables and give them a name, okay? So we have a gas occupying a volume of 752 milliliters. That must be our volume. That's the initial volume. So 725 milliliters at a pressure of 0.97. So that's our initial pressure, 0.970 atms. And they tell us at constant temperature. So since that's constant, I can get rid of it on both sides. And then it says it's allowed to expand until its pressure is 0.541 atmospheres. And then we want to know, what is V2? What is the final volume? So our combined gas law equation is P1 V1 over T1 equals P2 V2 over T2. Since the temperatures are gone, we actually get P1 V1 equals P2 V2. And we want to find V2, so I'm going to divide both sides by P2. And you get P1 V1 over P2 equals V2. Now it's just a plug and chug. We have our 0.970 atmospheres times our 725 milliliters all over our 0.541 atmospheres. The atmospheres cancel. I'm left with milliliters, and the answer is 1,299 milliliters. Now remember, 3 sig figs, so we should actually write this as 1.30 times 10 to the third milliliters. Alright, this problem is similar to the last. They tell us that a volume of gas is 5.80 liters measured at 1.00 atmospheres. And they tell us the pressure of the gas in millimeters. What is the pressure of the gas in millimeters? If the volume is changed to 9.65 liters, so our new volume is 9.65 liters. And we want to know, what is the new pressure in millimeters of mercury? They tell us that temperature is constant. So since temperature is constant, it falls out of the equation. Then we can rewrite our equation, our combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. Since T2 and T1 are constant, we get P1 V1 is equal to P2 V2. So P1 V1 equals P2 V2. We're looking for P2, so we'll divide both sides by V2. And that gives us P1 V1 over V2 equals P2. Then we can just put in our numbers. And so our pressure 1, we had 1.00 atmospheres. And then we had our V1 was 5.80 liters. And our V2 was 9.65 liters. The liters cancels. That gives us the answer in atmospheres. And then we're going to have to convert that to millimeters of mercury. So our answer in atmospheres is 0.601 atmospheres. Now remember, we got to convert that into millimeters of mercury because that's what the problem asked for. So we take our 0.601 atmospheres times 760 millimeters of mercury is 1 atmosphere. And when we do that, the answer is 457 millimeters of mercury. Alright, here we have another combined gas law problem. And it says an ideal gas originally at 0.85 atmospheres, so that's my P1, 0.85 atmospheres, and 66 degrees C, so I'm going to put that in there, 66 degrees C. was allowed to expand until its final volume, pressure, and temperature were all 94 milliliters. So our final volume was 94 milliliters, and our final pressure was 0.60 atmospheres, and its final temperature was 45 degrees C. Now what we're looking for in this one is actually what was the initial volume. Now, first thing we have to do is we got to remember all of our temperatures are in degrees C. We cannot use degrees C in any of our calculations because degrees C is not the absolute temperature scale. So we have to convert all of these into Kelvin. So I'm going to add 273 to both temperatures to give me our temperature in kelvins. So we get 339 Kelvin and 318 Kelvin respectively. So let us write our equation for the combined gas law. P1 V1 over T1 equals P2 V2 over T2. Now this time we're looking for V1. So what I'm going to do is I'm going to multiply both sides by T1. So T1 cancels out. I get P1 V1 is equal to P2 V2 T1 over T2. Now I'm going to divide both sides by P1. And that cancels out, and I get V1 is equal to P2 V2 T1 over P1 T2. Now we can just go ahead and plug in all of our numbers. So our value for P2 was 0.60 atmospheres. Our volume 2 was 94 milliliters. Our T1 was 339 Kelvin. And then our P1 was 0.85 atmospheres. And our T2 was 318 Kelvin. And when I do the math here, look, atmospheres cancels, kelvins cancels, I'm left with milliliters. So the answer is 71 milliliters. Now, ask yourself, does that answer make sense? Well, it tells us that the gas was allowed to expand. So it went from a smaller volume to a larger volume. So that definitely makes sense. Alright, in this problem, it asks us at 741 torr and 44 degrees C, 7.10 grams of a gas occupy a volume of 5.4 liters, and they want to know what is the molar mass of the gas. Now, they give us a mass, and they give us a temperature and a volume and a pressure. The key is that we can use the ideal gas law, PV equals nRT, to solve for the number of moles, and then use the mass to find the molar mass, because remember, molar mass is simply grams per mole. So if I know the number of grams and I know the number of moles, if I divide the number of grams by the number of moles, that's the molar mass. So let's take a look. What have we got here? Pressure is given as 741 torr. 741 torr. The volume was given as 5.40 liters. The temperature is 44 degrees C. We don't know N. And our mass was given as 7.10 grams. So the first thing I'm going to do is I am going to make sure that I've got all my units in what I need. Because remember, R, the universal gas constant, has a value of 0.0821 liter atmospheres per mole Kelvin. So my temperature needs to be in Kelvin, and my pressure needs to be in atmospheres. I don't have pressure in atmospheres, and I don't have a temperature in Kelvin, so I need to convert these first before I do anything. So 741 torr, well, remember a torr is just the same as a millimeter of mercury, so 1 atmosphere is 760 torr, and this gives us a value for the pressure of 0.975 atmospheres. And for our temperature, 44 degrees C, we're going to add 273 to get to Kelvin, and that gives us 317 Kelvin. So now I can take PV equals nRT and solve for N. So PV is equal to nRT. Divide both sides by RT. They cancel out. So PV over RT equals N. So now we can plug in all of our values for PV and RT to find the value of N. So 0.975 atmospheres times the volume of 5.40 liters, 5.40 liters, over R, 0.0821 liter atmospheres per mole Kelvin, times 317 Kelvin, and that's going to give us 0.2023 moles. Now I'm going to carry one extra sig fig here just to make sure that I get my most accurate possible molar mass. So once I've got the number of moles, I finally take my number of grams and divide that by the number of moles. So 7.10 grams over 0.2023 moles gives us a value for molar mass of 35.1 grams per mole. Alright, so this problem is a Dalton's law of partial pressures problem. And it says a mixture of gases contains 0.31 moles of methane, 0.25 moles of ethane, and 0.29 moles of propane. The total pressure is 1.5 atmospheres, and it asks us to calculate the partial pressure of the gases. Now, remember, Dalton's law says that the total pressure is equal to the sum of the individual pressures as if they were the only gas present in the mixture. So P total is equal to the pressure from gas 1 plus the pressure from gas 2, ... P to the n. Another way to look at this is the total pressure times the individual fraction of the gas gives you the individual pressure of the gas. So that's P1 is equal to Chi1 times PT, and you can do that for all the different gases that you have. So what we need to record here is we've got gas 1 is 0.31 moles of methane, and then we've got gas 2 is 0.25 moles of ethane, and then gas 3 was 0.29 moles of propane. And our total pressure is equal to 1.50 atmospheres. So, let's start with gas 1. The pressure of gas 1, P1, is equal to Chi1 times PT. So we need to determine what is the chi. So, remember, mole fraction, chi, is equal to the moles of component A or component 1 over the total moles. In other words, it's really just a percentage. So, to find the chi1, this is going to equal 0.31 moles over the sum total of all the moles. 0.31 plus 0.25 plus 0.29. And chi1 comes out to be 0.36. So we're going to take that times our total pressure, 1.50 atmospheres, times 0.36 equals 0.54 atmospheres, and that is for the CH4. Now we're going to follow suit with ethane and propane. So Chi2 is going to equal 0.25 over 0.85. So Chi2 has a value of 0.29. And we're going to multiply that times our 1.50 atmospheres times 0.29, and that gives us 0.44 atmospheres for the ethane, C2H6. And then likewise, Chi3 is going to equal 0.29 over 0.85 times our 1.5 so that we can get 0.51 atmospheres for the C3H8. Now, if you want to check that, the sum of all those, 0.54 plus 0.44 plus 0.51, should give us our original pressure in atmospheres. And you'll see that it comes out to be slightly less, and that is due to rounding of our numbers, because we only had two significant figures for our number of moles. So in this problem, it asks a certain anesthetic contains 64.9% carbon, 13.5% hydrogen, and 21.6% oxygen by mass. They also tell us at 120 degrees C and 750 millimeters of mercury that 1 liter of the gaseous compound weighs 2.30 grams, and they ask us, what is the molecular formula of the compound? So the first thing we have to do is, this is first an empirical formula problem. So by the video magic, we're going to pop up the empirical formula. And once we've done all that work, 64.9 grams of carbon, 13.5 grams of hydrogen, 21.6 grams of oxygen. We convert those into moles of each, divided by the smallest number of moles, in this case the 1.35 moles from the oxygen. And that gives us a ratio of 4 carbons to 10 hydrogens to 1 oxygen, or C4H10O. So that portion is strictly an empirical formula problem, just like we've done before. Now the important part here comes when we start dealing with the gas laws. So when we start dealing with the gas laws, we have some information. We've got the temperature is 120 degrees C. We've got a pressure equaling 750 millimeters of mercury. We've got a volume equaling 1.00 liter, and we've got a mass equaling 2.30 grams. So if I've got a temperature, a pressure, a volume, and a mass, I'm looking for a molar mass. And you have to have the molar mass in order to get the molecular formula from a compound from the empirical formula. So this is screaming out for PV equals nRT. So PV equals nRT. We want to find N, so PV over RT equals N. Now we need to make sure that we have all of our units in the correct form. So let's take a look at this with the correct formula and the correct units. Alright, so we've got our pressure in atmospheres, 0.987 atmospheres. We did that by converting it from millimeters of mercury to atmospheres. And we have our temperature is 393 Kelvin. If we plug that in and solve for N, with value of R being 0.08 to 1 liter atmospheres per mole Kelvin, we find that we've got 0.031 moles of gas. Now, to find the molar mass of the gas, I'm going to take the 2.30 grams divided by the number of moles, 0.031 moles, and that gives us around 74 grams per mole. So to find the molecular formula, we need to take this molar mass divided by the empirical formula mass. So our molar mass was 74, and our empirical formula mass, remember, we had 4 carbons, 10 hydrogens, and an oxygen, and that equals 74. So 74 divided by 74 gives us 1, so our actual molecular formula was the same as the empirical formula, C4H10O. Alright, for this problem, this is going to be a stoichiometry problem, but we have to make some assumptions. Dissolving 3 grams of an impure sample of calcium carbonate in hydrochloric acid produces 0.656 liters of carbon dioxide, and they tell us the temperatures and pressure which that was measured, and they ask us to calculate the percent by mass of calcium carbonate in the sample, and it asks to state any assumptions. Well, the first assumption we need to make is that the calcium carbonate in our sample is in our limiting reagent, so HCl is in excess. That, and because this is in solution, we're going to ignore vapor pressure of water and just assume it's negligible in our calculations. So, to start off, we need our balanced chemical equation. And from this, we can see that 1 mole of carbon dioxide comes from 1 mole of calcium carbonate. So what we're going to do is we're going to work backwards. We're going to find the number of moles of carbon dioxide and relate that to the calcium carbonate. So the first thing we need to do is we need to determine how many moles of carbon dioxide we have. So we've got a pressure that was 792 millimeters of mercury. We have a temperature measured at 20.0 degrees C, and we had a volume equaling 0.656 liters. So let's convert these into our standard units. So this is 293 Kelvin, and we have for the pressure 1.04 atmospheres. So we're looking for N, so PV over RT is equal to N. So that's going to equal the 1.04 atmospheres times 0.656 liters divided by 0.0821 liter atmospheres per mole Kelvin times 293 Kelvin. And when we do this, the number of moles we get is 0.02836 moles of CO2. Now we're going to take the moles of CO2 and translate that into grams of calcium carbonate. So our 0.02836 moles of CO2 times 1 mole of calcium carbonate for every 1 mole of CO2 times 1 mole of calcium carbonate has a mass of 100.1 grams of calcium carbonate. And when we do this, we find the mass of the calcium carbonate to be 2.84 grams of calcium carbonate. Now they ask us, calculate the percent by mass of calcium carbonate. Now we had 3 grams as our sample, but only 2.84 grams of it is calcium carbonate. So the percent by mass is going to be 2.84 grams over 3.00 grams times 100, which yields 94.7% calcium carbonate. Alright, so these are several different types of problems that you can run into. These are a lot more difficult than the ones we will be doing for the baseball event. For the baseball event, focus on doing your P1V1 over T1 is equal to P2V2 over T2, your combined gas law. Focus on your conversions between millimeters of mercury to atmospheres, atmospheres to torr, to pascals, to kilopascals. Focus on PV equals nRT, and there are some Dalton's partial pressure laws that could pop up as well. But really, if you get a good grasp on the ideal gas law and the combined gas law, you're going to do just fine.